This video is the third part of the section 8.6 video, and in this part we're going to actually use the vertex formula to find the vertex. That vertex formula is what we developed in the second part of this section 8.6 video. So if you watched the last section of this video, you know that we found out that for a generic quadratic equation, the x-coordinate of the vertex is negative b over 2a. Then we can find out what the y-coordinate is by plugging that back into the equation for x and finding out what y is. So now we're going to go ahead and do an example of that. We're going to start with f of x equals x squared plus 6x minus 5, and I'm going to find the vertex of this quadratic equation. So the x-coordinate, or the h part, is negative b over 2a. b is 6, and a is 1. So I get negative 3. Now to find the y-coordinate, or the k part of the vertex formula, we just take that negative 3 and plug it back in to the formula. So we have negative 3 squared plus 6 times negative 3 minus 5, which is 9 minus 18 minus 5, which is what? Negative 9 minus 5, which is negative 14. So the vertex of this parabola occurs at negative 3, negative 14. And just to add on a little bit more, I'd like to point out that we could write this down in vertex form now. This is a little bit of a bonus since the question didn't ask us to. The vertex form of this equation is x plus 3 squared minus 14. To get that vertex form, we're just taking the a, plugging it in for a, the h value, negative 3, and plugging it in for h, and the k value and plugging it in for k in the regular old vertex form of a quadratic equation. Now we have two examples for you to try. I'd like you to take each equation and write it in vertex form and state the vertex. You can use either completing the square or the formula for the vertex. So go ahead and pause the video and give those a try. And we're back. Let's go ahead and take a look at these two problems together. I decided to do the first problem by completing the square. So I have x squared plus 4x plus 7, and I'm trying to get this thing into its vertex form and state what the vertex is. So by completing the square, I start by replacing f of x with y, and then I move the constant over so that the x's are by themselves. So I have y minus 7 is x squared plus 4x. Then I find the magic number, which turns out to be 4, and I add that to both sides of the equation. That gives me y minus 3 equals x squared plus 4x plus 4. Now I factor the right-hand side, which is a perfect square. It factors as x plus 2 squared. And then I add that 3 from the other side back to both sides so that I have the y by itself. So y is x plus 2 squared plus 3. That right there is the vertex form of this quadratic equation. Now it's easy to read off what the vertex is. The x-coordinate is the h value here, which is always the opposite sign. So I have negative 2 and 3 as the coordinates for the vertex. For my second example, I decided to use the vertex formula just so that I could demonstrate both methods. I had g of x equals x squared minus 8x minus 2. So the first thing I did was to find the h from vertex form, or the x-coordinate of the vertex, which is negative b over 2a, so the opposite of negative 8 all over 2 times 1, which turns out to just be positive 4. Then k, the y-coordinate of the vertex, I find by taking that 4 and plugging it back into the equation for x. So 4 squared minus 8 times 4 minus 2, which is negative 18. That tells me that the vertex is 4, negative 18. Now I can take that information and plug it into the vertex form. Vertex form is always a times x minus h squared plus k. Now my a value was 1, so I don't really need to write anything there. My h was 4, and my k was negative 18. So the vertex form is y equals x minus 4 squared minus 18. Finally, we can do more than find the vertex and the axis of symmetry for a quadratic function. We can find the x-intercepts and the y-intercepts. I want you to think about the process of finding the x-intercepts from an equation. Over here on a graph, if I have some parabola and it crosses the x-axis somewhere, the x-intercepts are the values of those x-coordinates. But what's the y-coordinate at that point? If I'm here on the x-axis, the value of y is 0. So the process for finding the x-intercepts is to plug in 0 for y. Secondly, let's think about how many x-intercepts are possible. In the picture that I've drawn for this parabola, it crosses the x-axis twice. So I could have 2 x-intercepts, but I can imagine also drawing a parabola that has no x-intercepts, maybe one that opens up and stays up here and never actually crosses the x-axis. And I could even have one that just barely hits the x-axis, so that it comes down, touches, and then turns around and touches at only one point. So the number of x-intercepts that are possible are 2, 1, or none. You can't have more than that, and you certainly can't have less than none. The method for finding the y-intercept is really similar to for finding the x-intercepts. Let's think about it again here. I've got a parabola, and say it looks like this. And I'm interested now in finding the y-intercept, this point right here. If I'm sitting here on the y-axis, what's the value of x? Any of the points along the y-axis have an x value of 0. So in order to find the y-intercept, I will plug in 0 for x. And then finally, let's think about how many y-intercepts are possible. If you look at all of these pictures that I've drawn, they all have exactly one y-intercept. And that's going to be true for all parabolas. It certainly can't cross back over the y-axis. That would make it not a function anymore. And because it's a parabola, it's going to eventually hit the y-axis in one direction or the other. Now we're going to do an example where we put all this information together. We're going to find the vertex of a quadratic function, decide if it opens up or down, and then find any intercepts. Finally, we'll use all that information to sketch a reasonably accurate graph of this quadratic function. The first thing that we're going to do is find the vertex of this quadratic function. I'm going to use the vertex formula to do that. So remember that the vertex formula says that the x-coordinate, or h, of the vertex is negative b over 2a. So I take my b and my a, plug them into that formula. b is 2 and a is 1. Simplifying, this will give me negative 1 as the x-coordinate of the vertex. To find the y-coordinate, or k, we plug that negative 1 back into the equation. You could write that as f of negative 1 if you wanted to. I'm going to have negative 1 squared plus 2 times negative 1 minus 3. When I simplify all that, I'm going to get the number negative 4. So the vertex occurs when x is negative 1 and y is negative 4. Next, we're going to determine if this opens up or down. Looking at the equation, I see that the lead coefficient is positive, not negative, so it must open up. Next, we're going to find any intercepts. That means both x and y intercepts. We'll start with the x-intercepts. Remember that in order to find the x-intercept, I'm going to set the y equal to 0 and then solve for x. So I plug in 0 for the y, or for the f of x, equals x squared plus 2x minus 3. And now I start solving for x. This is a quadratic, so I'm hopeful that I can solve it by factoring. And sure enough, factors of negative 3 that add up to positive 2 are positive 3 and negative 1. And this gives me two equations. Either x plus 3 is 0 or x minus 1 is 0. So x is negative 3 and x is 1 are the two x-intercepts. Now notice we could write those as negative 3, 0, the point, and 1, 0 as an ordered pair. The last thing we want to do is find the y-intercept then. So to find the y-intercept, remember that this time we're going to set the x value equal to 0. That's because if you're on the y-axis, the x value must be 0. So I say y equals 0 squared plus 2 times 0 minus 3. And that simplifies really nicely to be negative 3. So that means that the y-intercept is the point where x is 0 and y is negative 3. Finally, we'll use all this information to sketch a reasonably accurate graph. Now the vertex happens at negative 1, negative 4. I'm going to go ahead over 1, down 1, 2, 3, 4. I know I have two x-intercepts where x is negative 3 and also where x is 1. And then I have a y-intercept where x is 0 and y is negative 3. So this gives me plenty of points to connect up to draw my parabola. There it is. Now the last thing I'm going to do is just label some things. That point right there is the vertex. The axis of symmetry, remember, is the line that cuts the parabola in half, so I can just draw it right in there. This is actually the line x equals negative 1, and it is the axis of symmetry. Before we move on from this example, I want to point something out to you. We found the vertex of this parabola to be negative 1, negative 4. And we also know that the parabola opens up. That means that the vertex will be a minimum value for this parabola. When x is negative 1, this parabola achieves its minimum value of negative 4. We're going to use that a little bit in the next problem. In this example, we're going to look at a ball that is thrown into the air, and its height after t seconds is given by this function. Now, this is a parabola. Let's decide if it opens up or down. Because my leading coefficient is negative, it opens down. Before I go any further, I'd like to make a quick visual of this parabola, just a really, really rough sketch. So this is a parabola that opens down. And the x-coordinates here are time, and the outputs are height. This next part asks me, when does the maximum height occur? Well, looking at my graph, I can see that the maximum height is going to happen wherever the vertex is. So what I'm looking for this first question is this coordinate, the x-coordinate of the vertex. And hey, we have a formula for the x-coordinate of the vertex. We can just plug it right in there, negative b over 2a, so negative 48 over 2 times negative 16, and that will be 1.5. So after 1.5 seconds, the parabola actually hits its maximum there. So this x-coordinate down here gives us the time when the parabola will be at a maximum. So 1.5 seconds is when the maximum height occurs. The next thing is to find the actual maximum height. In order to find out what this height is, I need the y value of the vertex. To find the y value of the vertex, I take my 1.5 seconds and plug it back into the formula. So I'm looking for the k, or the y value of the vertex, which is my function evaluated at 1.5 seconds. So I plug 1.5 in for my t. And after some simplifying, I think we should get 100 feet as the maximum height that the ball achieves. The trick to these problems that ask for a maximum or a minimum is to realize that they're really asking you for the coordinates of the vertex. And that wraps us up for section 8.6. Good luck with your homework.